In this video, we're going to look at two special cases of how to apply our method of partial fractions to be able to compute these integrals where the integrand is the ratio of rational functions. Whoops, this is a 1. Got a little messy. So the first special case is the case of improper fractions. In the previous examples, the degree of the numerator was always less than the degree of the denominator. Improper fractions is the case where that's not true. So in this case, notice the degree of the numerator is 3, which is greater than the degree of the denominator. Which is 2. So we're going to need to do polynomial division. And if you'd like a refresher on polynomial division, I posted a link to an additional video where you can watch how to do polynomial division. It's not necessary, but it's worth refreshing your memory if it's been a while since you've thought about polynomial division. So my scratch work, before we get started on integration, we have two things that we're going to do. The first is polynomial division, and then we can get into setting up our partial fractions. So I'm going to do long division. I'm taking this polynomial and dividing it by this polynomial. Something that I like to do because there are missing terms, I'm going to write x cubed plus 0x squareds plus 0x's plus 2, so I don't get confused about place values. Sometimes it's easier to miss these, that this numerator is equivalent to this numerator. And what am I dividing by? I'm dividing by x squared minus 1. So to proceed with polynomial division, I'm going to take x cubed and ask myself, x squared times what is x cubed? And really it's just x. So now I compute the multiplication, and down in this row I'm going to say x times x squared is x cubed, and x times negative 1 is minus x. And I'm lining up these place values, maybe I should say minus x, plus 0x squareds minus x. So now that I've performed the multiplication, I'm going to subtract. What is x cubed minus x cubed? 0. 0x squareds minus 0 more x squareds is still 0. And then 0x's minus negative x becomes positive x. Next step, I ask myself, x squared times what gives me an x? Nothing. I bring down this 2, and I see that this is too small, that x squared can't go into this, so this becomes my remainder. So it means that after computing polynomial division, my other factor is going to be x remainder x plus 2. That's a funny looking remainder. How do we rewrite this in conventional mathematics? This can be rewritten as x plus 2 divided by x squared minus 1, right? Because this remainder is actually the remainder, the number of pieces of x squared minus 1s that were left over after the division process. So what does this tell us? Let's go back to our original integral for this second. That's telling us that the integral of x cubed plus 2 divided by x squared minus 1 dx is equal to the integral of this function, which is x plus 2 divided by x squared minus 1 dx. And I can break this up into two separate integrals, but before I get there, now let's zoom in and look at the x is easy to integrate. I know how to integrate x. I'm going to make it 1/2 x squared. But this piece is harder to integrate. We're going to need to use the method of partial fractions just looking at this piece. So let's continue on with our method of partial fractions just looking at this piece. So this is again scratch work. I want to be able to rewrite x plus 2 divided by x squared minus 1 as the sum of fractions. My first step, this denominator isn't factored for me, so I have to think about how do I factor x squared minus 1. Notice that there are no middle terms. This ends up being x plus 1 and x minus 1. Those are sort of easy things to be able to factor. I can factor that in my head. And I want to be able to rewrite this as a divided by x plus 1 plus b divided by x minus 1. I'm not doing any calculus. I'm just using algebra to rewrite this ratio as the sum of two fractions. And I'm going to do this even faster. Like every iteration we make this go a little bit faster, right? So I can almost in my head, I know that because I'm adding fractions, it means that I'm going to multiply a by x minus 1, and I'm going to multiply b by x plus 1 so that I can get a common denominator. Notice I'm not writing out the denominators here because that's a lot of writing and it's something that's a little more than what I need to do. And I want this numerator to be equal to this numerator. So I'm writing a star here saying that these are just the numerators. And when you compute these, you can just write out the numerators as well, because there's a lot of writing, I know. To do the distributive property, this means that ax minus a plus bx plus b has to be equal to x plus 2. We're going to set up a system of equations by matching our like terms. Let's make sure that the coefficients on the x terms match. X is actually 1x, so that gives me the fact that one of my equations is going to be 1 is equal to a plus b, making sure that by combining like terms I get 1x. And then for our constant terms, we need to have 2 is equal to negative a plus b. And I'm going to do addition of equations here because I see that the a and the negative a will cancel. So adding this system of equations together, I get 1 plus 2 is 3. I get a plus negative a is 0, and b plus b is 2b. So that means that 3 halves is equal to b. Plugging that into this equation up here, I can say that that means, plugging it in up here, 1 is equal to a plus 3 halves, because 1 is equal to a plus b. So I subtract 3 halves from each side. 3 halves is actually 1.5, so I get negative 1/2 is equal to a. And we've completed our work. That means that these fractions can be rewritten as a is equal to negative 1/2 over x plus 1, and b is equal to 3 halves over x minus 1. So this scratch work set up our partial fractions, and I can go back to this integral right here and say that instead of writing this as the integral plus of x plus this one messy fraction, I'm going to rewrite it as the integral of x plus 1/2 of x plus 1 plus 3 halves divided by x minus 1 dx. I took this fraction and rewrote it as my partial fraction decomposition. So now we can integrate. This is the integral of x dx plus negative 1/2 times the integral of x plus 1, or 1 over x plus 1 plus 3 halves times the integral of 1 over x minus 1. And again, each of these pieces are individually really easy to integrate. The integral of x is 1/2 x squared. The integral of this, it's the really basic use substitution. This becomes minus 1/2 the natural log of the absolute value of x plus 1. And then finally plus 3/2 times the natural log of the absolute value of x minus 1 plus c. So notice that there was nothing fancy about this technique. The only hard part that I added in was the fact that we had to do polynomial division before we could do partial fractions, before we could do the really straightforward, easy integration. So let's consider another case, the case of repeated roots. Suppose that we had this integrand, x squared plus 11x divided by x minus 1 times x plus 1 squared. Notice that this x plus 1 factor is occurring twice. So just like we would see before, if I wanted to do a partial fraction decomposition, this single root I'll treat the way that I normally treat a single root, that it would be a divided by x minus 1. And continuing on, you would have another fraction that's the piece that you would have before, but how can we differentiate this between a partial composition of this? In addition to these roots, we could also have a fraction where I had x minus 1 squared as a denominator. So for repeated roots, you need to add in not just the x minus 1 and the x plus 1, but for each root that is repeated, I need to have each instantiation of that repetition. So you could imagine that if this were x plus 1 cubed, I would have to have the x plus 1 to the first power, x plus 1 to the second power, and I would have to add on an additional term, an x plus 1 to the third power. But that ends up being a lot of algebra, and I don't think that you need to see that for demonstration. So really, now we're going to proceed the same way that we've proceeded with our other integral processes, that I'm going to get common denominators of each of these fractions, and then I solve for my a's, b's, and c's. So because we're experts at this by this point, well, maybe not quite, I'm going to just look at the numerators, and I'm not going to worry about writing out the denominator each time. The denominator in this case is going to be the original denominator, right? Because I want to make sure that I have something common among each of these fractions. So in order to get this common denominator, I need to multiply a by x plus 1 squared, because I need to have a denominator of x minus 1 times x plus 1 squared. And then my next term, b, is going to need to be multiplied by both x minus 1 and x plus 1, because this denominator only has one factor of x plus 1, and I need to have two factors of x plus 1. And finally, my c term is going to be multiplied by x minus 1 to get the common denominator. So all of these numerators need to be equal to this numerator, which is the x squared plus 11x. Now we just have a lot of algebra to do. So for this first term, I have to do, notice that x plus 1 squared is not x squared plus 1 squared. I have middle terms, and if you wanted to, this is a common error, that's why I bring it up, that this is x plus 1 times x plus 1, and I have to do a distributive property. I end up with a times x squared plus, here there's x times 1 plus x times 1 becomes a times 2x, and then plus 1 times a is a. Moving on to this, I get bx squared minus x plus x cancels the middle terms, and then I have minus b. And finally, I get an easy one. I get cx minus c. It's all equal to x squared plus 11x. I'm going to write plus 0, because each of the linear terms are going to have to add to be 0. Now I'm going to combine like terms and set up my system of equations. Here I have ax squareds and bx squareds has to be equal to x squared, and there's a hidden 1 here, 1x squared. So that means that a plus b had to be equal to 1. I didn't have to worry about a c in there. Next, I have, what are my x terms? Here's an x term. I didn't have any bx terms, and a cx term is 11. So combining my like terms, that tells me that 2a plus c equals 11. And then finally, looking at the constant terms, a minus b minus c has to be equal to 0. A minus b minus c equals 0. Again, we have lots of methods for being able to solve this. Last time I had a system of 3 equations. I plugged it into my calculator. You could do that again. I'll do this one by hand because I think that that's another way that's possible to solve these. I'm going to eliminate all of my b variables because I can see using the first equation that a is equal to 1 minus b. So now anytime I see an a, I'm going to replace it with 1 minus b. Maybe this isn't the wisest variable substitution, but this is what I chose to do. So now I get 2 times 1 minus b plus c equals 11. So this is substituting this, plugging this into the second equation. And I'm going to simplify. 2 minus 2b plus c equals 11. Subtracting 2 from each side. Negative 2b plus c equals 9. I'm going to take this and also plug it into the third equation. So a minus, whoops, what is a? Sorry. I'm eliminating my a's. A's are equal to 1 minus b's. So I get 1 minus b minus b minus c has to be equal to 0. So this is 1 minus 2b minus c equals 0. And I'm going to add these to the side so everything becomes positive. That means 2b plus c is equal to 1. Now I have a system of 2 equations. I have this equation and I have this equation. I'm going to add these 2 together and I'm going to get negative 2b plus c equals 9, and I'm going to add onto it 2b plus c equals 1. I'm adding them because I see the 2b's and the negative 2b's cancel. So that means c plus c is 2c, 9 plus 1 is 10, c equals 5. If you're feeling a little lost at this point, just go back to the fact that we had 3 equations and 3 unknowns, and if you decide to solve using different variables, as long as your end solutions are the same, you've done your work correctly. Hooray! So now we found out a value of c, and we can plug that c value into any one of these previous equations. I'll just plug it in here because I think it's easiest. So we get that 2b plus 5 equals 1. I'm going to subtract 5 from each side, and I get 2b equals negative 4, right? 1 minus 5 is negative 4. So that means b equals negative 2. And then finally, if a equals 1 minus negative 2, that means that a is equal to 1 plus 2, which is 3. Nice. So, we did a lot of hard work, and what did we just find out? We found out that a is equal to 3, b is equal to negative 2, and c is equal to 5. And now we can finish doing relatively straightforward integration. Let's take a look. So this is now the integral of 3 divided by 1 minus x dx plus the integral of negative 2 divided by 1 plus x dx plus the integral of 5 divided by x plus 1 squared dx. But notice, unlike before, 1 over x, we can use natural log to integrate. This is a slightly different form, and it's not actually natural log of x or natural log of x squared. So this is something to be careful about when doing these repeated roots. These we can integrate in our head. I've demonstrated a couple of times. This is going to be 3 times the natural log of the absolute value of x minus 1 plus negative 2 times the natural log of the absolute value of x plus 1 plus, how do we integrate this? Let's go ahead and work through the steps of our u substitution. Here, maybe I'll do this work off to the side. Let's let u equal x plus 1. That means that du is equal to just 1 dx. So it's an easy u substitution. And now when I'm integrating 5 divided by u squared du, which is equal to the integral 5 times the integral of u to the negative 2 du. So when I integrate this, this becomes 5 times negative 1 times u to the negative 1 plus c, which is negative 5. And recall, what was u? X plus 1 to negative 1 plus c. So because my denominator was squared, it's no longer just the natural log of something. I can use power rule. I did a u substitution in power rule, and I got to see that this was plus negative 5 times x plus 1 to the negative 1 plus c. So this is the final example. This is my special example when you have an integrand that's a rational expression of which there's an irreducible quadratic factor. So in all of the previous examples, I've always been able to reduce it into something like 1 plus, or x plus 1 or x minus 3. Here, there's nothing I can do about this term over here, that x squared plus 2 can't be factored within the real numbers. Of course, we could go into complex numbers, but that's a whole different thing, and we don't want to get into that. So it means that when we do partial fraction decomposition, we have to account for that in our partial fractions. In this case, it means that I can do the first term, whoops, I should have an integral sign here. The first fraction is what we want it to be, but the second fraction needs to have a linear numerator. That because this x squared plus 2 is in the denominator, I need to make sure that the numerator has degree of 1 less than that. So this would be bx plus c. What am I saying? I have an irreducible quadratic denominator, and that means that the numerator is 1 degree less. In this case, it's the linear form bx plus c. And I guess I'm integrating this with respect to x. But the way that we proceed from here is the same method that we've been proceeding in the past. So let's go ahead and get common denominators. So in this case we want x, so this is my scratch. I'm not integrating here, I'm just getting my partial fractions. X squared plus 2. I'm not going to do as much in my head this time. This is a divided by x plus 1. I'm going to multiply it by x squared plus 2 divided by x squared plus 2. And then whoops, bx, sorry, that looks sloppy, plus c in the numerator. Can you read that? I'll change it. This says bx plus c in the numerator has the denominator x squared plus 2 times x plus 1. So now, ignoring the denominators, I know that x needs to be equal to ax squared plus 2a, and I also know that doing the distributive property, bx squared plus cx plus bx plus c. So all of these need to be equal. This x over here, notice what's hiding is that there are 0 x squareds, and there are also 0 linear terms. Let's go ahead and find all of our like terms. 0 is equal to x squared plus, so combining my like terms, I find the system that 0 is equal to a plus b, and then combining the x coefficients, there's actually a 1 hiding here. 1x, do I have any x's over here? Yep, they're equal to cx plus bx. So maybe 1 is equal to b plus c. And then finally, for our constant terms, 0 is equal to 2a plus c. So now I have a system of equations. You can solve using whatever methods you like. I'm going to go ahead and solve using substitution. I'm going to try to do a wiser substitution than I did before. Let's set a equal to negative b, and I'm going to go through and substitute 2a here should be equal to, then instead 0 is equal to 2 times negative b plus c, and that means that 2b is equal to c. I'm going to combine this information with this information. 2b is equal to c, so I plug in that into this equation. I see 1 would then be equal to b plus 2b, so that would mean that 1 was equal to 3b, and 1/3 equals b. If 1/3 equals b, then 2 times 1/3, or 2/3, equals c, and because a is equal to negative b, a is equal to negative 1/3. Whoops, we're a little off the page. But that was the hard part of my fraction decomposition. Let's go back and rewrite that. I can write in red, that means a is equal to negative 1/3, b is equal to 1/3, and c is equal to 2/3. So it means that my original integral can be rewritten. The integral of x dx divided by x plus 1 times x squared plus 2 is equal to the, I'll just write the coefficients out front, negative 1/3 times the integral of x plus 1. But this one is a little bit more complicated, right? That this is one single integral. So this is plus the integral of 1/3 x plus 2/3 divided by x squared plus 2. So I'm going to rewrite this numerator as two separate fractions. That's hard to do. You can't split up denominators, but it is totally fine to split up numerators, right? Because like 1/5 plus 2/5 is just 3/5 that you just add the numerators. So in this case, this is going to be the integral of 1/3 of x divided by x squared plus 2 dx plus the integral of, I'll throw the 2/3 out front, dx of x squared plus 2. We need to use different techniques to integrate each of them, and although they're easier than each of the individual pieces, it's still a little bit more complicated than just throwing natural logs in each of the places. So this first one, because I have a linear term in the bottom, this does end up being negative 1/3 times the natural log of the absolute value of x plus 1. This one's the easy one. This one here, though, I am going to do a u substitution. I need to see that u is equal to the denominator in this case, x squared plus 2. That means that du is 2x dx. I don't have 2 x's, so I'm going to multiply to get 2 x's, and then I'm going to multiply out front by 1/2. So now maybe I should continue this work downwards. We see that this gives me 1/6 times the integral of, I'm going to combine the 2x and the dx together, make my du, and x squared plus 2 is u. So notice that this is exactly what we want it to be, that the integral of 1 over u is the natural log of u. So this ends up being, maybe I should have a plus, 1/6 the natural log of u, and u is x squared plus 2. So let's not forget our first term. But this final one, we could do a u substitution for here. I can't really do a u substitution here. In fact, we're sort of at a loss. Really, we have to think back on what we did for our derivatives of inverse trig functions give us things that look like this. So that means that this actually is very similar to an arctan, right? And avoiding all of the messy work, really what we would need to do is I need to factor out this from each of the coefficients, because I need x squared plus 1. Debating, should I go? I'll go ahead and go through the steps because I think it's important to see as a review exercise as well. Let's do this on a separate sheet of paper though. So on my separate sheet of paper, I'm going to consider what is 2/3 times the integral of x squared plus 2. I'm going to rewrite this I need to factor out a 2 from each of these terms. So this is the same as 2 times 1/2 x squared plus 1, right? So I factored out a 2 from this x squared to make it 1/2 x squared plus 1. So throwing that 2 out front, this actually just becomes 1/3 times the integral of 1/2 x squared plus 1. Now I want to rewrite this 1/2 x squared as a single thing squared so that I can make my u substitution. So this 1/2 x squared could be rewritten as 1 over the square root of 2 times x, all quantity squared, plus 1. I know, messy scratch work. We're working on this one piece and it's looking like this. And now I can go ahead and make my u substitution. Let's let u equal 1 over the square root of 2x. du is the derivative of that. I don't have just a 1 over square root of 2 hiding anywhere. This is being used up for the u part. So somehow I need to multiply this by 1 over square root of 2, and that means I'm multiplying out front also by the square root of 2. So now I can actually integrate. Let's continue on over on this corner. I have the square root of 2 over 3. The 1 over square root of 2 and the dx become my du. And then I have u squared plus 1, which we're all done. This is arctan, or inverse tangent, of u plus c. And recall what our u is. This becomes square root of 2 over 3 arctan of 1 over square root of 2 times x plus c. Phew! So that means this final integral down here becomes plus square root of 2 over 3 times the arctangent of x over square root 2 plus c. Now I know that that was messier than you would have liked, that you were thinking, well, couldn't this be easier somehow? It turns out that's about as good as it gets.